Okay, in this chapter, we're going to be looking at telescopes, and that's going to include certain kinds of telescopes that are probably familiar to you, and actually some different kind of telescopes that you may have never even imagined before. Now, telescopes generally work by having the ability to take light from very far away and bringing it to a focus. And here we see a example of a refracting lens. This is called a refracting lens. Typically, these kinds of lenses are made out of glass or some kind of clear plastic. And what they do is you have light rays coming in from very far away, so far away that the light rays are essentially parallel to one another. And as the rays of light pass through the lens, they come to a focus. And this ability to bring the light to a focus is what enables telescopes and lenses to create images of things that are very far away. Now, the question is, how does this work? It has to do with the shape of the lens and the fact that as light goes through a different material at an angle, it will bend. And we've seen this sort of thing before where if we have a prism, you guys know that the white light will come into the prism and it'll bend down and it'll deflect. And the thing about prisms is that the different colors get bent different angles. That's why the colors separate. But the key thing here are the angles on the sides of the prism. And so the light's coming in straight and it comes in straight, it hits at an angle, and so it bends, and then it comes down here and it hits the second surface at another angle and it bends again. And so what you have is the net effect of these bendings is that the light bends. Now, the way that they design the shape of the lens is so that the light at the top bends a little bit more, the light just below bends a little bit less. The light going through the middle doesn't actually bend at all, it just goes straight through. But then as you go down, it bends. And if you get the shape just right, all the light will come to a point we call the focus point. In the previous slide, we mentioned that the kind of lenses that we were talking about are what are known as refracting lenses. And this is because they make use of the physical principle of refraction. Now, refraction is the bending of a wave. In this case, we're talking about light waves. It could be sound waves or some other kind of waves, but any kind of wave can do this, but we're talking about light waves, of course. So we have the bending of a wave due to a velocity change as it passes from one material or one medium into another at an angle. And so we want to just kind of get an idea of how this works. So here I've drawn a barrier between, say, air and glass. So this could be part of a lens that's made out of glass, and this could be the air on the outside of the glass, and I've got a beam of light coming in. Now the thing about glass is that when light passes through glass, it moves more slowly than it does when it's moving through the air. Think of like when you go swimming, if you're walking across a pool in the water, you move more slowly walking through the water than you do through the air. It's kind of the same idea for glass. That light, when it goes into the glass, it moves more slowly. And so what happens if this beam of light comes in at an angle? Well, what happens is you can see this corner of the light beam makes contact with the glass first, and this corner of the light beam hasn't yet made contact. So this guy slows down, but this guy's still going like gangbusters. He hasn't slowed down yet. And so what's going to happen is because it slows down until the entire beam is in the glass, it's going to bend because this guy's slowing down and it's like this guy's going to swerve. And so instead of going straight through, you might expect it to just go straight through like that. What's going to happen instead is that beam of light is going to bend. It's not going to go straight through. So the straight through path would be something like this, but instead it's going to be coming at an angle. And it's because the light slows down, one part of the light slows down while the other part hasn't slowed down yet, and that's what creates the bending effect. Now, of course, what happens if you're not at an angle? Then you have your beam of light coming in and all the parts of the light hit the surface at the same time. So there's no bending, and the light will just go straight through. And so when you have this lens kind of a shape, the light coming in up here hits at an angle, the light coming in here hits at another angle, the light coming here hits another angle. All these different angles create different amounts of bending. And so if you can make that shape just right, you get this guy bends a little bit more, this guy bends a little bit less, but they bend just the right amount so that over here they all come together at the same point. And that, of course, is that focal point of the lens like we were talking about. Now, the cool thing is you can do the same kind of thing with a mirror. Now, if you have a flat mirror, you know kind of how that works. The beam of light comes in and it reflects off the mirror. And if it's coming in at a steep angle or a narrow angle, you get different amounts of deflection. Basically, whatever angle it comes in at, that's the angle it's going to go out at. So down here you can see it's coming in at a narrow angle, and here it's leaving at a narrow angle. Here it's coming at a fatter angle, it leaves at a fatter angle. Now, you can make use of this principle by curving the shape of the mirror, almost like a funhouse mirror. Instead of being flat, it's curved. And so again, you have these parallel rays of light coming in, and where they strike, there's different angles of striking, so there's different amounts of bending. If you make the shape just right, all of these parallel rays of light will come to a focus right there. And this is a property that lets lenses and mirrors create images of things. And so that's really what a telescope is for. A telescope is a device that lets you bend light into a focus so that you can image it. And remember, we're detailing this particularly for rays of light that are parallel. The way that you get rays of light to be parallel is you simply have the thing making the light be very, very far away. Like, a star or a planet that's very, very far away. The light coming from those things is essentially always going to be parallel. And so these rules about how light bends works perfectly. So that means that we can use either lenses or mirrors or some combination thereof to create telescopes. And this slide is actually showing the two main kinds of telescopes. There's what's called a refractor, and that uses lenses, primarily uses lenses. Remember that principle of refraction, the bending of light through a lens or through a different surface. And then the other kind of telescope is what's called a reflector, and those are telescopes that use mirrors to bend the light to a focus. And so you can see the two different designs here. So with a refractor, that's the one on the left here, I've got my starlight, I'm looking at a star, it comes in, and I can use this lens to bring the light to a focus. And then what makes it a telescope is I can use a second lens to image my focus, and this guy acts kind of like a magnifying glass to blow up the image so that I can see it in my eye. Now, another kind of telescope uses mirrors to do the same thing. And so I've got my starlight coming in, and the starlight comes in and it bounces off this curved mirror here. It's curved in such a way so that all these parallel rays of light from the star will come to a focus. Now, normally, the focus of this mirror would be right here, but you wouldn't be able to see that very easily. I mean, you'd have to put your head right there and look down the telescope, but guess what? Your head would be blocking the light. You wouldn't be able to see anything. So what they do is they put a teeny tiny little mirror here at an angle, and this is just a normal flat plane mirror, and it picks off the light and sends it off to the right, and it's going to focus over here, and then you can use another little lens to image it on your eye so that you can see it. I very often tell my students to pay particular attention to this slide because I want you to be able to roughly sketch it out and sort of get the idea of how the two different types of telescopes work, the kind that use lenses and the kind that use mirrors. And so if you're in my class and you're preparing for a test, look at how these are designed. I mean, this one's basically a tube with two lenses. The light comes in parallel through the first lens, comes to a focus. It crosses through the focus and then comes to this lens and comes out to the eye. For the reflector, this was the refractor, this is the reflector. The main thing is that the curved mirror at the bottom, the light comes in, it hits a curved mirror, and it comes to the pick-off mirror and then goes out to the side where there's another little lens. So you can draw those different kinds of telescopes to kind of a rough sketch. I'm not an artist of any skill. I don't expect you to have tremendous artistic talent, but you should be able to sort of sketch the basic idea and understand how these two different telescopes work. Now, in this slide, it says modern telescopes are all reflectors. And if we were being really careful, we should probably add in the word mostly all reflectors. The reason for that is because telescopes that use mirrors have a lot of advantages over telescopes that use lenses. And here are some of the examples of different advantages that mirror-based telescopes have over lens-based telescopes. One of the key things is that light traveling through a lens is refracted differently depending on the wavelength. What that means is that the different colors of light focus at different places. And so when you're looking at an image that's through a telescope that uses lenses, the colors can get kind of smeared out together and it can make the image a little bit blurry. So that is something that you have to correct with additional lenses, and it makes the telescope more expensive and more heavy. And you can't really perfectly correct it. You can only kind of sort of correct it. Another problem with lenses is that some of the light traveling through the lens is absorbed. So I've drawn kind of a lens here. What happens is the light goes through the lens and it comes to the focus, and as it passes through the lens, some of the light just gets absorbed. Now with a mirror, when you have this curved mirror, the light comes in and it all reflects and none of it gets absorbed. And so that is an advantage that mirrors have over lenses. Another problem actually, and this isn't written down on the slide here, but what can happen is as the light comes in through the lens, it can actually bounce off the back surface, bounce off the front surface, and then go through. So you have the original beam that goes through and you have this reflected beam that goes through, and it can create sort of a double or even a triple image depending on how many times it bounces inside the lens. And if you have multiple lenses in your telescope, you can get lots of these bounces. Again, it distorts the quality of the image, and those multiple reflections in the lenses make them disadvantaged compared to mirrors, because with mirrors, there's no double reflection. The light comes in, it kicks off, and it goes away. Another problem with lenses compared to mirrors is that when you have very large telescopes, the lenses are very, very heavy, and you can only support them at the edges. What does that mean? Well, if I've got a mirror up here, I can just mount it to something at the back because only the front of the mirror interacts with the light. And so I can hold it up here. I could even, nail it to the wall or whatever even. But with a lens, and we can see a lens down here, I can hold it at the edges and the light can pass through. But if I try to hold it all at the back, the light's going to be blocked by whatever's holding the lens up. So you can only support it at the two edges, and that is why that's another thing that's problematic about lens-based telescopes. And the last thing that's noted on the slide here is that a lens needs two optically acceptable surfaces. Remember I told you you have to get the shape just right? Well, that's a lot harder than it sounds. And when you have a lens, you have to get the front surface the right shape and the back surface the right shape. With a mirror, you only have to get the front surface the right shape because the light reflects off of it. It never reaches the back surface. And so these are some of the reasons why mirror-based or reflecting-based telescopes are much more common these days than the kind that use lenses. Here we see the Keck telescope, which is a famous telescope in Hawaii. And it's actually built on a mountaintop. It's at the summit of Mauna Kea in Hawaii. And you find that is often the case, that telescopes tend to be built on the tops of mountains. Can you imagine why that would be? What would be the advantage of putting a telescope on the top of a mountain? Well, there are a few different advantages. One is that it helps you get up above some of the light pollution from the city down below. But the main reason is that it actually means that if you're on the summit of a tall mountain, the starlight that goes into your telescope has gone through less air than the light that would go through a telescope at the bottom of the mountain. And we've talked previously about how as light goes through the air, it interacts with the air and it gets distorted by the air. And so by building your telescope up high on a mountaintop, you can reduce some of the effects of the light passing through the air. Now, to do even better than that, you can put telescopes into outer space beyond the atmosphere. So there's absolutely no interaction with the atmosphere messing up the light. And so that is something that is a very useful thing. And here is a schematic of the famous Hubble Space Telescope, which has for decades been an amazing resource for astronomical research. And at the time that I record this video, the James Webb Telescope, which is sort of the successor to Hubble in many ways, was just launched, and it's creating some rather remarkable images for us to marvel at. The Hubble, of course, has made many, many important and beautiful images of things in outer space. And if you just Google images from the Hubble telescope, you'll treat yourself to some really beautiful astronomical images. Now, the main mirror on the Hubble telescope is about 2.4 meters in diameter, and it's designed for visible infrared and ultraviolet radiation. And so here we can see a comparison of the best ground-based image of the M101 galaxy at the bottom with the image from the Hubble Space Telescope, which is at the top. And we can see the image from the Hubble Space Telescope is actually a lot more detailed. That's in part because the light going through the Hubble telescope hasn't had to go through the air first. Now, when you're thinking about building a telescope, one of the questions that you might ponder is, how big do I need to make the telescope? And what are the advantages, if any, of having a bigger telescope versus a small telescope? Now, you might sometimes get the impression from what you read that bigger is always better, but it's not necessarily true. One of the things that having a bigger telescope lets you do is get more light scooped up into the telescope. And so if you're looking at something that's really dim, something that's very far away, for example, a bigger telescope really would be better for you. But if you're looking at something really, really bright, let's say you're looking at the Earth's moon, there are some advantages to having a much bigger telescope, but there are also some disadvantages because the moon is already so bright that if you look at it through a really big telescope, it could actually hurt your eyes. It can be uncomfortable to look at the moon through a really big telescope. And you have to put filters on the telescope to kind of block out some of the light so that it doesn't hurt your eyes. Sometimes you can get away with having a smaller telescope and get really good images, depending on what you're looking at. But for some things, you really need a bigger telescope. So in terms of how much light a telescope can gather up, the brightness it turns out it says in this slide that it is proportional to the square of the radius of the mirror. And you guys might remember from your high school math classes that the area of something circular, like a circular mirror, is equal to pi times the radius squared. And so when they say the brightness is proportional to the square of the radius of the mirror, they really mean it's proportional to the area. I don't know why they said it that way. But in any case, the bigger the area of the telescope mirror, the more light that it can collect. And so the brighter your image will be. And if you're looking at something that's dim, you want what you see to be as bright as possible. So here you can see two images taken of the same object with two different telescopes. And the telescope on the right over here was twice as big of an area as the one on the left. And so you can see the one on the left taken by the smaller telescope. You can see some good detail. You can see this thing over here that's bright, but look how much more you can see from the bigger telescope. All of this here you couldn't see with the smaller telescope. It was too dim. But the bigger telescope is able to gather enough light that you can actually see this detail in this structure, and you can see this other stuff here that you can't even see on the other telescope. Another thing that the size of a telescope impacts is what's called the resolving power. The resolving power of a telescope refers to the ability of a telescope to distinguish two objects that are close together as two separate objects. In other words, if I'm looking through a particular lens or a particular telescope at two objects that are really close together, if my telescope is too small, it might just look like one sort of blob. The light from the two things kind of overlap one another, and I can't really tell that there's two things there. It looks just like a blob. But as the telescope gets bigger and bigger, I'm better able to see, oh, there's two things there making light, not just one. And so you can kind of see this here. There's two objects that are emitting light, and when you look at the light through a small lens, you might just see just kind of all the light smears together. But as the telescope gets bigger, you start to see there's some structure there. And if the telescope is big enough, you can actually see, oh, there's two different things. They just happen to be close together. Now, this depends on two things. It depends on how big your telescope. It also depends on the wavelength of light. So it's easier, for example, to tell that two things are two separate things close together if you're looking at visible light, which has a shorter wavelength, than, say, infrared light, which has a longer wavelength. And so it depends on the wavelength of the light, but also it depends on the size of the telescope. And here you see 4 different slides of the same galaxy taken from 4 different telescopes with different resolving powers. And that just means that basically the mirrors or the lenses or whatever are bigger and bigger and bigger. And so the resolving power here is 10 arc minutes. This is 1 arc minute, 5 arc seconds, and 1 arc second. And basically what that's telling me, if I've got a lens here and I'm looking at two things that are close together, they're going to come and they're going to make an angle with that lens. And this, remember, angles are broken in degrees. You know, they're 360 degrees in a circle. But then each degree is subdivided into 60 minutes. And they call them arc minutes so that you don't confuse them with time minutes. But there's 60 minutes in a degree, and then there's 60 seconds or 60 arc seconds in a minute. And so these are the obviously, as the angle gets bigger, these two guys here would separate further away. And so these are this is telling you the angle of light that we can perceive here. And so this is showing that as the resolution gets better, that the detail in the image gets much more clear and you can see a lot more detail. The long and the short of it is, for seeing detail, bigger is better.